This video lesson is going to go through an introduction to our next concept, which is rational expressions. Just a little bit of background on the unit. The primary skill that will get you through this and lead to a successful completion of this is being very competent in your factoring skills. So how to find the greatest common factor, simple trinomials, difference of squares, hard trinomials. Those are kind of your four base ones. If you have those down, you will be fine. If you don't, you're going to require some probably extra work to get up to speed on your factoring skills. At this point, it would be assumed that if you've arrived at pre-calc 11 and you're ready to do rational expressions, that you can already factor. So we won't be going through factoring. And we did do a review of it before we did our unit on quadratics. So we have reviewed it all this year. You could go back and find some extra practice if you needed it. Okay, so we're going to start just by showing you what a rational expression is. So let's go back here. It's basically fractions, and these will be algebraic fractions. So they're going to be fractions that have variables in them. You've done fraction work before, and we're going to do a lot of the same fraction work you've done before in middle school even. The only difference being our fractions are going to look like these types of things down here. See how you see the difference now, how you have variables in either the numerator or denominator or both. So in order for it to be a rational expression or an algebraic fraction, so it's got to be a fraction with a polynomial numerator. Now a polynomial could be a single term, just a number, could be a single term like this, just a variable. It could be multiple terms like this, but there are some criteria when you do have variables. They can't have negative exponents, and they can't have fraction exponents. They have to be positive non-fraction exponents in order for us to consider it a polynomial. Your denominator, now it adds here, you'll notice, get my pen ready here, you'll add that it, or notice in the denominator it adds, it has to be non-zero. Well, I think we all know the reason for that is that if you had a fraction, let's say 3 over 0, well, we've always been told you can't have 0 in the denominator because that's undefined. So that's why they stipulate that the denominator has to lead to a non-zero polynomial. And we'll talk a little bit more about that here in a moment. So these are just kind of some samples of the types of fractions that you're going to deal with in this section. Okay, so moving on to the first thing that we're going to be responsible to do is learn how to figure out what values of the variable are not permitted. And you said, what do you mean by not permitted? Well, we talked about how the denominator of the fractions is not allowed to be 0 because that would make that fraction undefined. So when you're going to have a situation like this where you can pick what you're going to put in for x, well, you have to make sure that you don't put something in here for x that would make the bottom of this fraction become 0, because then this whole fraction would be considered undefined. So over here you'll see a box. This is right out of your textbook. They refer to, sometimes our book calls them non-permissible values. Over here, non-permissible values. Some books will call them restrictions. They'll say state any restrictions or state any non-permissible values. They're both asking you to figure out what are the values for the variable that you could not let x, y, whatever letter is in the rational expression be, so that the denominator does not ever equal 0. So let me just give you an easy example here. For example, if you had x plus 2 over x minus 3, x can be any number we want it to be. That's any, with rational expressions, your domain, meaning what could x be? It's always this. But then there are exceptions. So there'll be a comma, except x cannot be, and then we'll determine, well, what could x not be? So if I go back to this easy one they had over here, and remember, we're only worried about the denominator being 0. You can have 0 over a number, that's fine. You just can't have some number divided by 0. That's undefined. So if I had this fraction, my concern would be, well, what would I put in the bottom, x take away 3, that would make the bottom become 0? Well, that answer would be 3, because if I had 3 in here, it'd be 3 take away 3, the denominator would be 0. So my non-permissible value would be that x could not equal, in this case over here, x could not equal 3. Now they're saying if x equaled 3, it would make the bottom 0. So the way you would write that as a non-permissible then is to say, given this rational expression here, x could be any real number, except x could not be 3. And this would be what we refer to as our non-permissible, or as I said, sometimes called a restriction. And so both of those words mean the same thing. Okay, so if I go to my examples, I got a few of them here we're going to do. All I'm doing to figure these out is I'm saying, okay, the denominator is not allowed to be 0. So what I'm going to figure out is what will make it 0. Okay, so all you have to do is set the denominator equal to 0. That's how you determine non-permissibles. So in this one, again, I don't care about the numerator, just the denominator. So what would make the denominator 3x minus 5 equal to 0? So I solve this. Divide by 3, divide by 3. So this tells me that if I let x equal 5 over 3, the denominator is going to equal 0, which means then my non-permissible for this question is x is not allowed to be 5/3. And you can see that if I was to put 5/3 in here for x, I'd get 15 over 3, which would be 5. Take away 5, that would make the bottom 0. The denominators of fractions are never allowed to be equal to 0. So that would be your non-permissible. So some of the denominators are going to be more than just, that was linear. This one is a polynomial. So this is where I referred to earlier, your factoring skills become critical. So you say to yourself, okay, what would make the denominator equal to 0? I say, okay, this is a quadratic equation. I need to figure out two numbers that would multiply to give 30, and the same two numbers, when I add them, I would get a negative 13. Well, those two numbers would be x subtract 10 and x subtract 3. Negative 10 times negative 3, there's your plus 30. Negative 10 plus negative 3, there's your minus 13, which tells me then if x was 10 or if x was 3. Either of those would make this become 0. Well, if they make this become 0, that means they make the denominator become 0. And they're not allowed to make the denominator become 0. So once you figure out the two numbers that make the bottom 0, you say x is not allowed to equal 10 or 3. And those would be your non-permissibles for that particular question. And again, notice I've ignored I don't care about the numerator. It is more than welcome to become 0. It's just the denominator of these rational expressions that is not allowed to be 0. So we go through the process of figuring out what would make it 0, and then the answers we get are the ones that we rule out and say x cannot be those values. Okay, so that, a few more just to, we'll go through real quick here. So these are, I think I got 6 of them here. I want to look at these, and I wanted to get non-permissibles. Right, so if I looked at the first one, it's linear. So I say, okay, what would make 8x plus 16 become 0? 8x. So you just move your number over there, divide by 8, divide by 8. So if x was negative 2, the bottom would be 0, which means x is not allowed to equal negative 2. That's my non-permissible. Quadratic. So this one I'm going to factor. I'm going to try and find two numbers that multiply to give negative 24 and add to give minus 10. And that would be a negative 12 and a plus 2. Okay. What would make those equal 0? Well, those would become 0 if p was 12 or if p was negative 2. So that tells me that p cannot be either of those numbers because it would make the denominator of the fraction become 0. Now this one's easy because the only thing down here is just a single x. It doesn't matter what the exponent is. I'm just saying, well, what would I put in for x that would make the bottom become 0? Well, the only number you would ever put in here to make the denominator become 0 would be 0. So this one, I mean, I can do just by inspection, say x cannot be equal to 0 because that would make this go undefined. If you have multiple variables, you're going to have to consider both. So for example, this one, and again, look, I don't even consider the numerators. All I'm ever looking at is the denominators for non-permissibles. I've got x multiplied by y, and I want to make sure that when I multiply those two together, I never get 0 on the bottom. Well, again, this is one you could do by inspection. X could never be 0 because if you had 0 times, I don't care what y is, 0 times anything is going to be 0. Y could never be 0 because 0 times whatever x is would also give me 0. So in this case, x cannot be 0, and the letter y cannot be 0. So there was a restriction or a non-permissible associated with each of those variables because they both showed up in the denominator. This was a little unique too because I have x minus y, two variables, and I'm trying to figure out, well, what would ever make x minus y become 0? So it is linear. Well, so let's just move that over there. So you can see here that if x was ever equal to y, so if x and y were ever the same number, and if you think about that, so let's say x was 5 and y was 5. Well, yes, 5 take away 5 would be 0. So I can't have that happen. So the way I would state my non-permissibles here is I say x is not allowed to be the same number as y. That's the only criteria that I have. X and y can be any other number. They just can't both be the same number. Otherwise, the bottom of our fraction becomes 0. And one last one, so another quadratic one. This one's set up for another one of your factoring strategies that hopefully you're confident in. That's the difference of two perfect squares. So you would factor out the bottom, x subtract 2, plus 2. So what would make that equal 0? Well, that would equal 0 if x, oops, didn't want to do that. If x was equal to 2 or negative 2. Negative 2 would make this bracket 0. 2 would make this bracket 0. If either of these two brackets were 0, because they're getting multiplied together, the answer would turn out to be 0. So that leads me to say that x could not be 2, nor could it be negative 2, because either of those would make the denominator become 0. Negative 2 or plus 2. You'll also see this written. I think you've probably seen this before. You can just put plus or minus 2. That covers both of them. Okay, so that's the first thing. Number one, I want you to just be familiar with what I'm talking about when I say a rational expression. So we're talking about fractions involving variables. The next thing I want you to be able to deal with is how do I figure out what values for the variables are not allowed? So we refer to those as non-permissibles or restrictions. And the final thing I'm going to look at in this video is how do I reduce fractions? We're essentially at the point now where you would have hit kind of your fraction work in middle school. So again, it sounds fancier. Simplifying is a fancy word for reduce. We're going to learn how to reduce fractions. And for the most part, students say, oh, I've already done that before. That's nice. And you have. You've reduced fractions involving numbers. You probably haven't had to reduce too many fractions that involve variables. So the goal of reducing is to figure out any factors that divide out so that the only thing left common to both the numerator and denominator is either a 1 or a negative 1. Again, I don't want to overcomplicate it, make that sound too complicated, but I find if students see an example. So in order to do this, basically what you're going to do is you're going to, as I said earlier, this is a key, you're going to factor everywhere you can first. That's the very first thing you're going to do. Then what you're going to do is you're going to divide out common factors. And I'll get to that in a second. Let's go down here and just look at reducing fractions with what you would be familiar with from, let's say, middle school. So for example, 8 over 10, if you had that fraction, hopefully at this point in your math career, you wouldn't leave that as an answer. You'd say, oh, well, 8 divides by 2 and the bottom divides by 2. Therefore, this reduces to 4 over 5. Well, the math behind what's really going on there is you're saying, well, 8 is equal to 4 times 2. 10 is equal to 5 times 2. That demonstrates that both of those have a factor of 2 in them. So what you end up doing is you divide out the 2's. Now, we're going to start talking about a term that's used in mathematics called canceling. It's one of the more powerful terms you can get your brain wrapped around, but it's also a very dangerous one because students get carried away with canceling and start crossing out things that you're not allowed to cross out. So what we're going to do is we're going to divide. I'm going to use the word divide for now, and I'm going to divide out common factors. Now that will evolve to, it's almost like a slang word, that will evolve to us talking about canceling out common factors. So essentially what we do is we look at this one and say, oh, hey, they both are multiplied by 2. You're allowed to divide out common factors. So basically what you do is I'm going to divide the top by 2, and I'm going to divide the bottom by 2, and that leaves you then with just 4/5. The reason they call it canceling is because when you have the picture in front of you like this, really what you're doing is saying, hey, they both are multiplied by 2, cross out, eliminate, divide out, cancel out the 2's, the common factors. So what I ended up doing was I canceled. Now the key here is one word. I canceled common, I'm going to put it in capital letters, factors. You're only ever allowed to cancel common factors. So for example, I'll give you one more just with numbers. If I had the fraction, I don't know, let's say 12 over 30. I could say, well, we can look this over the way, here's how we do it now. We say, well, 12 and 30 are both divisible by 6. That's the biggest possible number that goes into both of them. And we divide the top by 6. We would divide the bottom by 6. And we would say that this is the fraction 2/5, and we would, of course, be correct. Well, the visual mathematics behind it, and again, we're just doing this to get us set up for how we're going to do this with algebra, is we're saying that really 12 is 2 times 6. 30 is 5 times 6. I notice that they're both multiplied by 6, which means it's a common factor. You can divide out, cancel common factors. So I canceled out or divided out the 6's, and the only thing left was the 2/5. So that's mathematically how we've reduced fractions since back in middle school. So we're going to apply basically the same thing, but the key is we have to be able to write our numerators and denominators as factors. They have to be things multiplied together. So here's what happens. Students will see this and they'll miss part of it. So remember what step 1 is before you start doing anything. No, now remember, canceling was not step 1. So divide out all common factors. That's the step that will, again, some kind of fancy mathematical people would really frown upon using the word cancel because they said a lot of times when students use that word, they don't have a clue what they're doing. But it's a really commonly used term in high school to get rid of common factors. It's called canceling out. But the key is to realize that they're common factors. So if I go to this one, step 1 is factor, the numerator and denominator. They're factored separate. It's like 2 separate questions. Look at this one. It's only got 2 terms in it. When you have 2 terms, you really only have 2 options: greatest common factor or difference of squares. The first thing on any factoring strategy is always supposed to be GCF. That's the one you should look for first. And this, both terms are divisible by 5, and they also have an x in them. So this one would have a GCF of 5x. After I divide out 5x, I'm going to have x subtract 4. So this numerator is 5x multiplied by x minus 4. The denominator, I see a GCF of 10 and also x. When I take out that, I'm going to be left with x plus 2 as my other factor. So if you look at this, you end up with, in the numerator, 3 factors. Now somebody's going to say, what do you mean 3 factors? Because the 5 is multiplied by the x, they're considered factors. Then they get multiplied by x minus 4. As long as there's no addition or subtraction separating these, so for example, in this bracket, these are considered terms because they have a subtraction separating them. You're not allowed to divide or cancel terms. You are allowed to divide or cancel factors. So one of the first things you got to make sure you can distinguish is what's the difference between a factor and a term. I'm going to underline, this is a factor, that's another factor, and then this whole thing is a factor because the 3 of those are multiplied together. The 10 is a factor, the x is a factor, and this is considered a factor. You're allowed to cancel out factors that are the same. So for example, this x and this x, I can cross those out. This x and this x, I cannot cancel out because they are terms, not factors. So how do you know the difference? Because they're separated, these two, by an addition and subtraction. That makes them terms. Now I do have this 5/10. Well, that's just a regular old 5/10 fraction like we would have done here. So we reduce it like we would have in middle school. 5/10 is 1/2. So what I end up with is 1/2. The x's are gone because I've crossed them out. There was an x in both numerator and denominator. And then I'm left with x subtract 4 over x plus 2. So someone might write it that way, which is fine. Now somebody else may write it, or might check an answer key in the back, x minus 4, 2 onto x plus 2. Now it doesn't look exactly the same as this, it's the exact same thing. Because if you have a 1 here, essentially you're going to multiply it through. Well, if you multiply something by 1, you're just going to get that back. The 2 would go through here. So I just left it as 2 times that. But sometimes you might see some people that actually multiply these together. You don't have to. There's no benefit to doing it. So this would be the reduced version of this fraction, or the simplified. I factored, and then I divided out or canceled any common factors. That's the way you always reduce algebraic rational expressions. You factor the numerator, factor the denominator, and then you divide out any common factors. The key is to get to the point where you get here and you realize this is a term, this is a term. I can't cancel those out. I could cancel the whole thing out because altogether it would be considered one factor, but I couldn't cancel just the 4 or just the x because they're terms. Down here, I could not cancel this x or this 2. I could cancel this 2 because it would be considered a factor because it's multiplied by this bracket. It's that big difference between factors and terms. Now, I'll just backtrack, and once students kind of learn this canceling process, sometimes they get really carried away with it, and they come here and say, oh, look at this, let's cross these out. Well, I can't do that. And why not? You said we could cancel factors. 20 is multiplied by x, 20 is multiplied by x, they're factors. But if you look at the big picture, this 20x is separated from this with a subtraction. That makes this a term and this a term. You can't cancel out a term or a piece of a term. So for that reason, you could not cross out those 20x's because of the addition and subtraction separating these two. Now, hopefully, as we do some more examples, you'll see the difference between factors and terms. Okay, so we'll kind of speed things up a little bit. Now, sometimes you're going to start out with monomials. Monomials, which is fine, you're allowed to have monomials. That means the numerator is all just one expression. So how do I know it's a monomial? If there was a plus between these two, now it's a binomial. Binomial means it has 2 terms. So I got back in the last slide, we were talking about terms and factors. Because there's no addition or subtraction in either of these two, both the numerator and denominator are considered monomials. Well, with monomials, all you do is divide numbers first. So you do your coefficients. So if you'd had the fraction 4 over 6, just reduce it like you normally would. So 4/6 would reduce to 2/3. Now, with variables, we don't want negative exponents. We mentioned that earlier. Rational expressions do not have negative exponents. So the way we deal with this here is I look and I say I have x to the 3. Well, x to the 3, if we were to write this out longhand, means x times x times x. That's x to the 3 in the numerator. Well, in the bottom, I have x to the 4. So that means x times x times x times x. Well, the math behind it is this x will cross out. These are factors because they're multiplied together. I'm allowed to divide out common ones. So that x would cross that x out. That x would cross that x out. That x would cross that x out, leaving us 1x in the denominator. Now, we don't want to write this all out for every time, but I want you to see the math behind why it happens. All we're going to look at is say, okay, in the numerator, I have 3x's multiplied together. In the denominator, I have 4x's multiplied together. The math behind it is these 3 in the numerator are going to divide out or cancel out 4 from the bottom. So what I do is I say, those 3 are going to be gone, and there's going to be just 1 left in the bottom. So it's going to be an x left down there. That takes care of the x's. Now let's look at the y's. So I would have 5 y's multiplied together, one after another in the numerator. I would have 2 y's multiplied together in the denominator. So the 2 from the bottom are going to cancel out 2 from the numerator. So I say to students, so how many are going to, where's there more? in the numerator. How many more? 3 more. So that means the numerator is going to be y to the 3. Now it goes right back to let me show you my eraser here for a second. Your laws of exponents from NERV 10. If I just use laws of exponents, well, laws of exponents says if you're dividing and you have the same variable, you just subtract exponents. So in the x's, it would be 3 take away 4, which would give you a -1. Well, x to the -1, again, we learned in NERV 10, is really the same thing as 1 over x to the +1. That's why I don't want negative exponents in rational expressions. So if you did it out, just let's say student B did it with laws of exponents. So 4 over 6, 2/3. They subtracted the exponents here, they get x to the -1. They subtract the exponents here, they get y to the 3, which would be great with one small little problem. I do not want negative exponents when I'm talking about rational expressions. So all I do is say, well, x to the -1, if you move it to the denominator, it would become x to the +1. So you just write it as 2/3. The negative exponent goes to the bottom and switches to the corresponding positive, and y to the 3. And again, negative exponents, sometimes for students it's a struggle, but it is something you've seen in grade 10 math. So that's just another way to arrive at that same one. I kind of like the canceling strategy myself. It avoids the whole negative exponent issue, but if you're more comfortable with that, that's up to you. So let's have a look at this one. Start with your fraction 6 over 12. That would reduce to 1/2. Let's go to the x's. I would have 5 x's in the numerator multiplied together. I would have 2 x's multiplied together in the denominator. So the 2 from the bottom will divide out 2 from the numerator, meaning there would be 3 still left over. There's 1 y in the numerator. There's 3 y's in the denominator. So this 1 y would cross out 1 from the bottom, but there would still be 2 left over. So there would be y squared left in the denominator. So this is the reduced or simplified version of those two rational expressions. So those are two examples that involve nothing but monomials. There was no addition or subtraction. Okay, so now let's look at the scenario where we're reducing rational expressions that have polynomials, so many termed, multiple terms involved in both numerators and denominators. Okay, so this one, the numerator. Now these are going to rely upon basic factoring strategies. And I know some of you are probably a little slower at these, but trust me, we're going to do a lot of factoring, or you should anyway, if you do the correct amount of practice over the next couple of weeks to get yourself up to speed on your factoring strategies. This is difference of squares. Difference of squares is factored by going x subtract 2 multiplied by x plus 2. They're called conjugates. Try and find two numbers that multiply. It's a simple trinomial because it's got a 1 in front. Two numbers multiply to get -8, add to give -2, x take away 4, x plus 2. They would multiply to give -8 and add to give -2. And then I think if you're good at factoring, you're going to find this really easy to do. Now all you look for are two factors, one in the numerator, one in the denominator, that are the same, that would be able to divide each other out or cancel. So you see an x plus 2 here and an x plus 2 here. Those are gone. X minus 2 over x minus 4 is the reduced version of this. Now this simply means that if you were up here to take x equals 1 and fill it in, or go down here and fill in any, I'm picking 1 as an example, but if you were to fill in a number here and get an answer versus me filling in a number here and getting an answer, you're going to get the same answer because these two fractions are equivalent. It's like having 3/6 and somebody else having a half. You say, well, they're the same thing. Well, this fraction and this fraction are the same thing. One is the reduced version of the other, using algebra to reduce them. I should go back and just, I'm not going to do this every question, but we should always be looking at non-permissibles if they're asked. It wasn't asked here, but let's just do it just for the sake of, so if once you do your factoring, non-permissibles, you can usually do by inspection, meaning looking at the question. You say, what would make this bracket become 0? Well, if x was 4, I'd have 4 take away 4, which would be 0. I can't have that. So x couldn't be 4, and x couldn't be a -2, because -2 would make this bracket 0. Notice I didn't look at the numerator, even though x plus 2 appeared up there as well. I only looked at the denominator. So these would be what we call the non-permissibles. So sometimes the question will say, reduce or simplify the following rational expressions, state all non-permissibles. That's what they mean right there. And you always state non-permissibles, notice, before you cancel. So the non-permissibles were before I cross things out. This next one's a unique situation that you should get familiar with. It happens quite frequently. It's when you've got the same two terms, except they're subtracted in the opposite order. So if I have x take away 4 and 4 take away x. Now there's a few ways you can kind of go through it. What I would like to show students, what if, remember x is just taking the place of a variable. Let's put a number in there instead. Let's put in there 7. If I had 7 minus 4 in the numerator, but the denominator was 4 minus, remember x is here. So this is what I filled 7 in for the x. I filled 7 in where the x is. Whatever you put here, you have to put here because x is the same thing. Well, 7 take away 4 would give me 3. 4 take away 7 would give me negative 3. When I divide those, I would get a negative 1. Now then I would always ask students, do you think it would matter what number I put here? Do you think it would be any different if I put, instead of 7 in there, I put a 10? 10 take away 4 would be 6. 4 take away 10 would be negative 6. Do you think that that's something that always happens? If you take any two numbers and subtract them, and then take the same two numbers but subtract them in the opposite order, do you think you're always going to get one the positive and the other the negative? And usually when students kind of look at it and say, hey, yeah, that is what's going to happen. Which means if you ever see this, x take away 4, divided by 4 take away x, you can simply cross them out, and the answer is a negative 1. Because the numerator and denominator are always the exact same with one exception. Either the numerator is positive and the denominator is negative, or vice versa. The numerator is negative and the denominator is positive, because they're always going to be opposites. Now, some mathematical ways to show that besides just kind of using your number sense is with factoring. So for example, x minus 4, you can take out a negative 1 as a GCF, which will switch it to minus x plus 4. Then your bottom is 4 minus x. Well, minus x plus 4 could be rewritten as 4. You switch the order of them. Well, now these are exactly the same. They cross out, and notice you're left with a negative 1. So that's if you use factoring to take out a negative 1 as a GCF. Now, to me, I suggest you just kind of, as soon as you see a binomial subtracted in the opposite order, that you just cross it out and put negative 1. Now, you have to be careful of this. I'll show students that and say, yep, I get it. And then all of a sudden, a day later, they'll run into x plus 5 and 5 plus x. And they'll say, oh, yeah, I remember he told us that when they're in the opposite order, you cross them out and you put negative 1. I'll say, no, that is not what I said. I said that if you have binomials subtracted, I want you to, let's go back to this. If I have addition, pick a number. If you had 7 plus 5, or you had 5 plus 7, does one turn positive? Or sorry, does one become the opposite sign? No, if you take two numbers and add them in the opposite order, you still get the same answer. So x plus 5 and 5 plus x, they don't divide to give you negative 1. They cross out. They're exactly the same, and they give you a positive 1. It's only subtraction you have to worry about that. All right, so keep that one in mind moving forward. We'll run into that lots over the next few weeks. Okay, so here are a series of simplifying, which again, if it was class, we'd kind of give you the chance to try them on your own. So if you want, you can kind of pause the video, write down these 4 questions, and try and reduce them on your own. And then I'm going to go through the answers here below them. So if you're going to try them on your own, pause the video right now and try and reduce these 4 fractions and put them in what you would think is their reduced version. Okay, so I'm going to go through the solutions to these 4. I think I even got a couple more maybe after these. This one's already factored, so I don't have to do step 1. So I'm just going to look this over and say, do I see any factors that are the same? Well, right away, I tried to give you a chance to remember the one from the last slide. Well, I got x plus 5. There's no other x plus 5s up here. I've got x take away 7. There's no x take away 7 down here. So there's nothing to cross out numerators and denominator with those. However, I've got this 3 take away 4x and 4x subtract 3. That's that situation we just talked about. They're the same two terms, just subtracted in the opposite order. I am allowed to cross them out, but I just got to realize that I don't divide them out to get a 1. I would divide them out to get a negative 1 because they're subtracted in the opposite order, leaving me with negative 1 multiplied by x minus 7 over x plus 5. So that would be fine. Now, hopefully your number sense is evolving to the point where if you looked in the back of the book and saw this instead, you'd say, oh yeah, okay, they just distributed the negative into here. This is the same thing. It's fine. Both of them are right, whichever way you would choose to write it. All right, so that one I didn't have to do the factoring. It was done for me. This one is not factored. So we're going to have to factor this out. Let's see what we can do. The numerator, when you have two terms, you need to realize there's only two possible strategies for factoring. Greatest common factor or difference of squares. That's it. There's only two. First one you always look for is GCF. Well, I notice both of these are divisible by 7. So I'm going to take out a 7. That will give me 2 minus x. Down here, two terms. Difference of squares, which it's clearly not. That's not a perfect square, nor is 2. GCF is the only other option. Take out, now I have an x cubed and an x squared. So if you have the same variable in both terms, you always take out the lowest exponent. So in this case, I've got x to the third and x squared. The GCF is going to be x squared. When I take that out, I'm going to be left with an x here and a minus 2 here. All right, just to make sure we get it ingrained in our brains, here's that same situation I ran into here and on the last slide. I've got the same binomial, just subtracted in the opposite order. I am allowed to divide them out, but I get negative 1. So now I have negative 1 multiplied by 7, negative 7, and the denominator would be x squared. This fraction is the reduced version of this fraction. Okay. Numerator, 2 times again, GCF. So we're going to take our GCF of 3, leaving me with 3a minus 1. Now, the denominator here is a hard trinomial. There's no greatest common factor. It's got a coefficient other than 1. With a hard trinomial, it usually takes a couple of steps to do them. So what I will often do with these ones is just kind of off in the margin, do my factoring, and then I'll put the factors down below here, just so I don't have to keep writing the fraction out over and over. So I'm going to take 3a squared plus 11a minus 4, I'm going to factor it. So this is a good chance to remind you how to do hard trinomials. Hard trinomials, you multiply the coefficient by the last term, and now you try and find two numbers that multiply to give negative 12, and the same two numbers have to add to give the number in the middle. Now, you make two brackets underneath here. Pay close attention to this. It's not the same as a simple trinomial. If it's 3a squared, you start with 3a and 3a. If it was 5a squared, you'd put 5a and 5a. 7a squared, 7a and 7a. Now you try and find those two numbers that multiply to give this one and add to give this one. So in this case, it would be negative 12 multiplied by a plus 1. Multiply those, you get that. Add those, you get, oh, I got that backwards. It should be plus 12 and minus 1. Because I wanted them to add to give plus 11, not minus 11. So this should be, nope, should be a minus. Get rid of that. 3a minus 1. So 12 times negative 1, there's my negative 12. 12 plus negative 1, there's my plus 11. So my signs are right. Now, you're not finished here. I find students when they get to rational expressions, they'll stop here and say, okay, there, I factored it. No, it's not factored. There's one more step. That's why I'm doing it over here, because I gotta write it out multiple times. What you now do is, at the very least, one of these brackets, sometimes both, will have a GCF in them that you have to not take out to the front, but you actually divide it. So I'm going to divide by 3, and this one doesn't divide by anything, so it's good. So this factor becomes a plus 4, and this one is 3a minus 1. So these are the factors of the denominator. So I'm going to go over here now and put them underneath this. A plus 4, 3a minus 1. Now, you have to understand that rational expressions are no different than regular fractions. You might have a fraction. When they're small numbers, it's usually easy enough that our math can tell us by looking at it whether they reduce or not. But if you had a fraction like 137 over 513, you might not be able to tell just by looking at it that it doesn't reduce, but it may in fact not reduce. Well, these are the same. You may do some work here and maybe nothing crosses out. So be it. It doesn't reduce any further. It's already a reduced fraction. Now this one will reduce a little bit because you've got 3a subtract 1 and 3a subtract 1. So they divide each other out or cancel, leaving us with 3 in the numerator and a plus 4 in the denominator. There's the reduced version of this fraction. Okay, here's another one. So this one's a simple trinomial and another simple trinomial. And nice, small, easy numbers. Two numbers that multiply to give 7 and add to give 8. Well, it's hard to screw this one up. The only way to multiply and get 7 is 7 and 1. And luckily they had to give you 8, so it factors. X plus 7, x plus 1. Multiply to get negative 5, add to give minus 4. That'll be negative 5 and plus 1. Notice a common factor. X plus 1 is in both the numerator and denominator. So the reduced version would be x plus 7 over x take away 5. Just to backtrack, again, it wasn't asked, but just in case, if I was looking at, I'll pick this one as an example. For non-permissibles here, x could not be 5 because that would make this 0 or negative 1. It would make either of those brackets on the bottom become 0. I look at this one for non-permissibles. A couldn't be a negative 4. Now this one here, sometimes students might have to say, what about if it's 3a minus 1? What would make that equal to 0? Well, if you bring your 1 over, a could not be 1/3. So your other non-permissible here would be 1/3. So you can always, if asked, state non-permissibles before you cross out any common factors. And again, you only look at the denominator when you're determining non-permissibles. I think these are the last two I've got. So these ones, if I looked at the numerator, it's close to the pattern of a simple trinomial, but there's one key thing that I always try and instill in students' heads when they're trying to factor polynomials, especially three-term ones like this. You never want negative in front of your x squared. So students, oh, I can't do anything about it. There's a negative there. Yes, you always can. If you factor out a negative 1, what it does is switch the signs of all of these. So now I'm going to write it in this pattern like the one in the bottom. The bottom's perfect. I'm going to switch it now to, instead of negative x squared, it's positive x squared. Instead of plus 3x, this will be minus 3x. And instead of plus 10, this is minus 10. But the key here is you always want your x squared term to be positive when you're using your factoring strategies. The negative 1, that's fine. We'll just leave it hang around out front and it'll come along and be part of our solution. But now this is the pattern of the factoring strategies that we've worked through. The bottom is fine. It's already positive, so I'm going to leave it the way it is. Now we're going to factor. Two numbers, multiply to give minus 10 and add to give minus 3, so be minus 5 and plus 2. Leave your minus 1 here. Factor this to be x subtract 5, x plus 2. Factor this to be x, so I'm going to multiply to get 8 and add to give 6. That would be 4 and 2. So x plus 4, x plus 2. So x could not be equal to negative 4 or negative 2. Those would be non-permissibles. I'm going to cross out any common factors I found. So this one and this one are the same. They cross each other out, leaving me with a reduced version or a simplified version, which would look like this. Okay, one more. This one is difference of squares. I find for whatever reason students want to, if they have 9 minus x squared, in their heads they think of it as x squared minus 9. You can't change the order of these. The order is 9 minus x squared. So I have to factor them in that order. It's square root of the first, subtract square root of the second, square root of the first, plus square root of the second. And I find students often want to write it as x minus 3 and x plus 3. They, for whatever reason, they want the x to be first. Well, I can't do that unless the x is first, which it's not in this one. So my difference of squares would look like this. Simple trinomial. I want to multiply to get negative 12 and add to give a plus 1. X plus 4 and x minus 1. That's not right. X plus 4 and x minus 3. Plus 4 times minus 3, there's my minus 12. Plus 4 and a minus 3, there's my plus 1. Okay, let's look this over for, let's just state them without actually writing them out. Non-permissibles, x couldn't be negative 4, x couldn't be 3. Didn't ask that, so I'm not going to write them out, but I'm just going to mention it. Now I'm going to look for common factors. 3 take away x and x subtract 3. Same two numbers, same two terms, subtract it in the opposite order. I can cross them out as long as I realize I don't get 1, I get a negative 1. That negative 1 will multiply by this. This is the reduced version of our original rational expression. All right, so that was kind of the essence of two things today that I want you to be familiar with. How to determine non-permissibles of a rational expression, and how do I reduce rational expressions. And we started out with a couple of monomial ones, quickly evolving into ones like this, involving polynomials, where you've got to use your factoring strategies that you've accumulated in grade 10 and in the first unit in this course on quadratics. As I said, moving forward, we're going to next learn how to, just like you would have in middle school, we're going to multiply and divide fractions, and then we're going to add and subtract fractions, and it will, in all of those situations, be very dependent upon your ability to factor. So I suggest using your textbook for the first little bit. Here are a series of questions from your textbook that will go through simplifying rational expressions. Again, I'm not saying you have to do all of these questions, but you need to do some of these questions for sure to make sure that you're practicing the skills to simplify and identify non-permissibles for rational expressions. All right, so we'll end this video here, and our next lesson will involve multiplying and dividing rational expressions.